Imagine, just for a second, the sheer, staggering weight of a modern commercial airliner. We're talking hundreds of tons of metal, cargo, and passengers just sitting there stationary on a runway. And then, picture that exact same massive machine soaring effortlessly at 35,000 feet. Like, how is that actually possible? Well, welcome to this explainer. Today, we're going to take a continuous, high-speed visual journey right through the beating heart of modern aviation, the jet engine.
Okay, let's dive into this. Because to really answer how this mechanical titan commands the sky, we can't just, look at the outside of it. We need to shrink ourselves down and track the incredible, violent, and frankly brilliantly orchestrated journey of a single air molecule as it travels from the very front of the engine all the way to the back. It is literally a masterpiece of thermodynamics in motion.
Now, before we zoom all the way in on our little air molecule's journey, let's look at the overall layout, which gives us a really clear mental map of the engine's major components, going from front to back. So we start over on the left with the intake and that massive fan, right? Then we move into the compressor, then the combustion chamber right there in the center, followed by the turbine, and finally the exhaust nozzle over on the right. Try to keep this anatomy in your head as we follow the air flowing through the whole shebang.
So the entire journey of our air molecule is governed by a fundamental thermodynamic rhythm. Engineers call it the Brayton cycle. And look, while the engineering terms might sound super complex, it's actually just a continuous, never-ending loop of four really simple processes. It's sucking the air in, squeezing it during compression, banging it with heat addition during combustion, and blowing it out through expansion and heat rejection. Basically, suck, squeeze, bang, blow. And it all starts at the very front.
All right, our journey begins as subsonic air is drawn smoothly into the engine's intake. But once it's inside, boom, the air hits the compressor. This component is made of multiple stages of rotating blades and stationary stators. And as our air molecule is forced through this continuously narrowing path, it gets aggressively squeezed. It's packing immense pressure and potential energy into a very, very tight space. Now, what's really interesting here is understanding just how mechanically difficult it is to compress this incoming air. Aerodynamicists use a brilliant analogy for this. Imagine trying to push water up a steep inclined channel using only rapid brushstrokes. You're forcing the air from a low-pressure area into a high-pressure area. And if that incline gets too steep, the water, or in this case, the air, wants to rush right back down. That's an adverse pressure gradient, and it is an absolute beast to fight. And because fighting that adverse pressure gradient is so incredibly difficult, it takes a monumental amount of energy just to run the compressor. Just look at this number, 70. Get this, between 50 to 70% of the massive power output generated by the turbine, which is later in the engine, is used solely to drive the compressor at the front. No way, right? It's a super hungry component, but it's absolutely crucial. Okay, so once our air molecule survives the brutal squeezing of the compressor, it enters the combustion chamber. Here, a lean mixture of this highly compressed air is sprayed with fuel and ignited. But actually, scratch that. Unlike your car's piston engine, where explosions happen in a confined, pulsing space, this is a continuous, flowing fire. The heat is added at a constant pressure without building up any additional pressure in the chamber itself. The engineering required here is just extreme. The temperatures inside this continuous fire hit roughly 1300 Kelvin. And to put that into perspective, 1300 Kelvin is literally the absolute metallurgical limit for standard turbine blades. So to survive this inferno without melting into slag, engineers have to design these blades with exotic superalloys, thermal barrier coatings, and these really complex internal cooling passages that basically bleed off cooler air just to keep the metal intact. Let's move to the next stage and see how this builds, because our air molecule, which is now superheated and highly energized, exits the combustor and hits the turbine. And here, the physics completely flip. We enter a favorable pressure gradient. So instead of being pushed up a steep hill, the expanding gases are now rapidly rushing down a pressure gradient. It's exactly like water flowing violently down a declined channel, slamming into the turbine blades and spinning them like a giant high-speed reverse windmill. The turbine's vital job here is to extract that kinetic energy from the hot, expanding gas. And because it's connected to the exact same shared central shaft as the compressor, this rotary motion sends massive mechanical power straight back to the front of the engine. This is the beautiful, self-sustaining loop of the gas turbine, right? The turbine powers the compressor, which in turn feeds the turbine. Which brings us to the final stage of our core thermodynamic journey, the exhaust nozzle. After the turbine has extracted just enough energy to keep that compressor spinning, the remaining hot pressurized gas accelerates out the back of the engine. By converting this remaining energy into a high-speed jet of kinetic energy, we invoke Newton's third law. For every action, there is an equal and opposite reaction. The gas blasts backward, and the aircraft is thrust forward. Now, what we just described is a classic turbojet, where 100% of the incoming air goes right through that fiery core. These were used in early aviation and fighter jets. They're incredibly fast for sure, but man, they are incredibly loud and fuel-hungry. So modern commercial aviation uses a different design, the turbofan. In a turbofan, a massive fan is added to the front, which takes most of the incoming air and simply bypasses it completely around the outside of the engine core.
So the crucial point here is that a turbofan generates a much higher mass flow rate with a lower output velocity. Basically, instead of shooting a small amount of incredibly fast, deafeningly loud air out the back, a turbofan pushes a massive amount of slightly slower air. This one change radically increases propulsive efficiency, it saves a tremendous amount of fuel, and it substantially reduces the deafening noise of the engine.
We actually measure this efficiency using something called the bypass ratio. A modern high-bypass turbofan might have a ratio of 10-to-1. That means for every 1 kilogram of air that goes through the fiery core to keep the engine running, 10 kilograms of air are pushed around the outside by the fan, and remarkably, in modern engines, up to 85% of the total thrust propelling your airplane is actually generated by this cool bypass air, not the fiery jet exhaust. Kind of mind-blowing, right?
But engineers are always pushing the limits, which brings us to the geared turbofan. In a traditional engine, the giant fan and the turbine are on the exact same shaft, so they spin at the same speed. But a massive fan is actually most efficient when it's spinning slowly, while the turbine wants to spin incredibly fast. So by inserting a planetary gearbox between them, engineers effectively decoupled their speeds. The fan spins slower for peak noise reduction, while the core turbine spins faster, squeezing out even higher thermal efficiency. It's a total game changer. And this brilliantly illustrates what's going on behind the scenes. Now, I know these engineering diagrams might look a little complex at first glance, but they really just illustrate the scientific reality of the journey we just took. They visually map the continuous loop, the compression, the heat addition, and the expansion. It's the visual proof of our engine's heartbeat. From the pressure rise during compression to the energetic release in the turbine, it perfectly validates that continuous thermodynamic loop we just traveled.
So let's put it all together in one seamless, continuous sequence. Our little air molecule is swept into the intake and immediately split by the giant fan. If it goes into the core, it is brutally squeezed by the compressor, fighting up that adverse pressure gradient we talked about. It gets sprayed with fuel and ignited in a 1300 Kelvin continuous fire. Then it rapidly expands down the favorable pressure gradient, slamming into the turbine to keep the whole machine alive, before finally being blasted out the exhaust as pure thrust. From the Wright brothers' early flights to the towering geared turbofans of today, the ability to manipulate pressure, temperature, and bypass airflow is exactly what allows hundreds of tons to soar safely above the clouds. Honestly, the next time you look out an airplane window at that massive engine, you're going to know exactly the fiery, perfectly orchestrated storm happening right inside. As you soar through the sky, propelled by this absolute masterpiece of thermodynamics, it kind of makes you wonder, what other invisible forces are shaping our modern world? Keep exploring, and thanks for joining this explainer.